All right. So if you are here, you are going to see Data Science Retreat Batch 30 Demo Day. So I thank you for your attention the next 1.5 hours and kind of congratulate you because I think you're going to learn a lot. It's a good use of your time. There are some projects here that are pushing what is possible right now with machine learning in applied settings. And I encourage you to do questions for anything that comes to your mind during the time they are speaking on the chat or after. So what is Data Science Retreat? So we are a training company that has been in the market since 2014, so earlier than most. We get people who have on average 5 years of experience already programming or in STEM fields and push them really hard until they produce a project that solves a real problem with machine learning. And this is what you're going to see here. This is Demo Day. This is where you see the output of a batch of DSR participants. How do we do this? We get trainers from industry that teach the one thing that they know very well and leave. So we have 23 trainers that do 400 hours of class. Each of them covers a topic that they know very well. And it's very intense. There are classes on weekends. There are 8 hours per day of class that is pretty intense. If you come here, you are going to condense the learning that will happen otherwise in about a year in 3 months' time. And we cover topics that are probably not in industry yet, but they will be there soon. So we don't prepare you for the interview that you will get in a company today in Germany. We prepare you for any interview anywhere in the world and with topics that will be relevant 2 years from now or maybe even longer. Why? Because this field moves very fast and it's not possible to train only the concepts that are around today. So if we will do that, then you will need to be retrained in 6 months' time, in a year time. And that's not the way we think about training. So if you know somebody who may want to transition into machine learning or data science, and they don't know about us, please tell them. After what you see here in the projects, I hope you're going to be convinced that there are many interesting things that you can do if you dedicate your life to machine learning. You can solve real problems from real people and with very little investment. What you will see here are projects that were executed in maybe 3 weeks and conceived over 3 months. Finding the problem that you're going to solve is half of the battle or more. The technical solution is kind of at this point easy enough that you can consider that the problems will come from somewhere else, not really from the difficulties that technology brings, right? And we will help you with the entire process, from finding the question to answering the question and presenting the results. Okay, so now we're going to go through different projects. The first one is called Q&A Engine for Healthcare. This is a project by Sina, Mariam, Manali. It's an all-female team, which is very good for me. So because we've been pushing very hard to get parity with genders in DSR, and we're getting close to it in this batch. So here you go.
Hi, we are Manali, Mariam, and Sina, and we have been working on how to build a medical Q&A system. Our work was accompanied by our mentors, Tristan and Markus, Thank you very much. Our distinct goal was to build a Q&A engine that is able to answer questions that are asked every day in primary healthcare. For example, can I still work out with a sore knee? Or I have a cold, why don't I get antibiotics? And we wanted our engine to answer, well, like a healthcare professional, natural sounding, detailed, and explanatory. We think that such a tool could be great in situations where no physician or pharmacist is available, or also in situations where barriers make communication with healthcare professionals difficult, or if pharmacies want to provide their patients more services. And last but not least, it's a cool tool to show healthcare professionals what AI can do. Let's jump right into how we solve that problem. Here you see the basic structure of our backend. When a question is asked, it first passes a classifier which decides if it's a healthcare question or not. If it's not a healthcare question, the questionnaire is made aware that the engine is built to answer healthcare questions. And otherwise, if it's a healthcare question, the question is passed to a text generating model of your choice. Let me now explain how this classifier, the filter, works. We had to build it completely on our own. And because it's a supervised learning task, we needed, well, a labeled data set. We had, on the one hand, many healthcare questions. That was the easy part. But we needed, on the other hand, diverse questions except healthcare questions that didn't exist. So we took a diverse data set with questions like the Stanford question and answering data set and manually labeled it. And we put together a data set that was well balanced. On text data, our classifier couldn't be trained on. So we needed some pre-processing steps. And what first happens is that each sentence, each question is broken down into word pieces or subwords, and then mapped to a vocabulary so that every sentence is represented as a sequence of numbers. And then it passes a language model, the Dilbert model, which understands language very well. And we, in simplified words, extracted with that model the meaning of each sentence represented as an embedding vector with 786 dimensions. And if sentences have similar meanings, they have closer numbers in their vectors. And that's something our classifier could work with. And we first tried a very simple model, a logistic regression model. And we were really surprised that we achieved such a good result. An accuracy of 98%, wow, that's cool. And we were happy because that's good enough for our task. And we asked ourselves, why did that work so well? And visualized what the Dilbert model returns and used a computationally beautiful trick and projected those large vectors with over 700 dimensions down to 2D, which means that each sentence, the meaning is represented by two numbers now, and plotted the density of the different kinds of questions. And you can see in this visualization that, well, that's the question types are almost linearly separable in 2D. if a question is on the upper left side, it's very likely a healthcare question and vice versa. And what works well in 2D works even better in over 700D. And that's why our model had such a high accuracy. Okay, question is classified now. What happens next will explain you Mariam.
Thank you, Sina. So now I will walk you through how we implemented the answer generation model. For this, we decided to use text generation models. And one of the most powerful text generation models are a family of models called generative pre-trained transformers, in short, GPT. These models are developed by OpenAI and use the decoder part of the general transformers as an autoregressor to generate text. So they predict the future words based on the past words. Their best model, GPT-3 DaVinci, with 175 billion parameters trained on 45 terabytes of data, is now able to do to generate coherent text. It can even write poems, and it can even code. So we decided to use this model and explore its capabilities to answer health-related questions. But we also wanted to use a model that we could train on a local machine on a single GPU. And GPT-3 is not open source, and even if it was, it's so big that we cannot handle it on a single GPU. So we looked for the biggest model that it was possible to be trained on a single GPU, and that was GPT-2 Medium, which is available by Hugging Face Transformers. So we selected this model. And for fine-tuning, we collected a list of question answer pairs from websites that provide this type of question answer pairs related to health. And we also explored this data. We found out that the data from WebMD has a higher quality. So we decided to go in two paths. First, we decided to train the model on WebMD, which has a higher quality, and also to use all the data. To use all the data for the training. And we generated our training samples starting with the start of text token and ending with an end of text token to show the start of and end of the question answer pair. We wrote a question keyword and followed the question byte, and the same for the answer. We ran the training for WebMD data and all the data and took the model with the lowest validation loss. For GPT-3, we experimented with prompt engineering. First, we just simply asked our question from the model. That's called zero-shot learning. Second, we provided the model with 5 question answer pairs, and then we followed by our question. This is called few-shot learning. And then finally, we interacted with the model via text. We gave the model some instructions and then asked the model our question. And the instruction were like the length of the answer that we want to have, and that we want to have a scientific answer. And finally, we use different decoding methods. So GPT at each stage outputs a probability distribution for different words. A greedy way of decoding is that we take the word with highest probability, but this does not result in the best sentence or sequence. So we try different decoding methods. We try to sharpen or flatten the probability distribution using a parameter called temperature. We use beam search so that instead of getting the word or token with the highest probability, we chose the sequence with the highest probability. And we also use top K and top P parameters that limit the set of tokens that can be used in total for text generation. So we experimented the model's output with all these parameters and took the best setting. And finally, we evaluated the model's performance using 85 questions, and the team's domain expert Sina rated each answer with subjectively by the amount that the answer was harmful or useful. And then what we can observe here from the scores of different models is comparing GPT-2 and GPT-3, we see that GPT-3 has a score of 1 point higher in general than GPT-2. Looking at the GPT-2s, we see that fine-tuning improved the score so by 0.3 point. But we also see that fine-tuning with all the data compared to WebMD only did not improve the performance of the model, pointing to the importance of the quality of the data that we use for training. And for GPT-3, we see that when we provided the model with instructions about the length of the model and the style of the answer, it gave us the best answers. So we selected that setting for our GPT-3. And now Manali will show us how the model performs in action.
Thank you, Mariam. So now architecture with our front end, we have created our front end with using Anvil tool, which is based on Python language. So front end will select or accept the request from the user as a question and transfer them to the backend, and backend then from backend, front end will display the answer to the user. So next is our result with respect to GPT-2 model and as well as GPT-3 model. So the question is, how should medicines be stored? So first one, answer by an expert. Second one, answer by an GPT-2 model. And last one, answer by GPT-3 model. So you can see here, our both model, GPT-2 and GPT-3 are performing very well, giving the best results. So the next question, why don't I get antibiotics when I have a cold? So answer by an expert, it is saying that antibiotics are generally not effective against the viruses. So you can read the answer by GPT-2. It is a horrible, like it is suggesting that you should take the antibiotics every day. So it can be very harmful. But you can see the answer by GPT-3 model. So it is quite good and also similar with answer by an expert. So very informative. So next is live demo with Anvil tool. You can find our web application link here. So this is our web application. And of course, we are dealing with the diagnosis and medication. So there is a disclaimer. So now we will see what happened with non-healthcare related question. So if I ask, how is the weather in Berlin? Oh, so it is classifying very well. So it is not related to healthcare question. So guys, if you have any question in your mind, like healthcare related question, then you must ask to our model. We are happy and so excited to see the results. Yeah, quite nice question. How can I treat a sunburn? So the answer is by GPT-3 model. So you can read. It is a quite good answer. Like sunburn can be effectively treated with variety of topical agents that are available over the counter. It is quite good result. So yeah. the audience, yeah, audience with online, they can also ask us questions, healthcare related questions. Let's just ask a question. How's going? How it's going? Tina. Yeah. How it is going? Yeah. Please ask a healthcare related question. Any other question from audience? Yeah, Aziz. No, you can ask. When to use ibuprofen?
Somebody from the chat says, "What is the secret of the universe?"
First, you can ask this question. When to use ibuprofen?
It's interesting because it's I mean, a challenging question.
Yeah, it is quite good.
Yeah, it is. I mean, it's actually, yeah. Yeah, actually you can take both for almost the same, and that's what the model says. So yeah, the answer is correct. It's quite good. Let me submit a second time because there's some variance between the answers always. Yeah, that's also good. It depends on the person's specific situation and health history. Fever aspirin is a better choice since it can help reduce the fever. However, that can ibuprofen do too. Ibuprofen also reduces fever.
Yeah, it is a quite good answer. And you can see below some links.
I wouldn't have rated with 2 or 3, I think. I don't like the answer. Yeah. Recreate, yeah, of course. When to use aspirin or ibuprofen was the when to use aspirin or ibuprofen was the question.
Somebody asked, is aspirin good for fever?
Yeah. Well, I don't like the answer that much. That's better, seems to be better. Yes, it's good for fever because it's a pain reliever and fever reducer, that's true. Yeah, that's not too bad. Not a very good answer, but it's not too bad. Yeah.
Let's ask a question a little longer. For example, I have a fever. Am I dying?
That's also interesting. Am I dying? Yeah, it's a very good answer. So you know you're not gonna die, but if your fever is high or lasts for more than a few days, you should ask your doctor.
Can you just ask, am I dying?
Sure. Everyone is dying, sorry.
Yeah. I'm curious what GPT-2 answers to this question. Okay, that's completely
It's too funny.
yeah. So okay, should we continue with our slides or?
You can continue. There's one technical question, but it's better to have it after you finish the
Yeah.
last slide.
Okay, cool.
You can click here. Now, Sina will take you through the conclusion and next steps.
So as you saw, the factfulness is not always guaranteed, but the model is often very correct. What could have been also better is the quality and quantity of our training data. So we would have ended with a better open source model. And also you have to pay for using GPT-3. It costs about 1 cent or a little bit less for every request. And if you want to train an open source model, that's also costly. It would start when you want to train, let's say, GPT-J with 6 billion parameters, it would start with a few €100. And you can go up to open end. We think that our application is absolutely not ready to get into hands of patients, but it would be a very valuable tool. For example, if a pharmacy uses messenger systems to communicate with patients and they ask questions, it would be a cool tool to generate a few answers and then maybe modify one of them slightly and then copy paste and send a text. I can imagine that would save 1 or 2 minutes for each answer. And let's imagine a pharmacy receives 30 questions, submits for every question 3 times, then it would cost €1 a day, or maybe a little bit less, and you would save 30 to 60 minutes. That's a good trade-off, right? So we think that's already a cool tool to use in practice. Our next steps is we want to really train a larger open source model like GPT-J with 6 billion parameters, and we're very curious about the outcome. We also want to deploy our application, how it is now. And another idea is to implement a translation pipeline so the app is available in many different languages. And another cool idea is to implement, for example, a feature that you can upload pictures and get an estimate. So you're very welcome to have a look at our GitHub repo or also on our LinkedIn profiles. And thank you very much for your attention.
All right, so if you see on the slide that is about to go out, Sina was a pharmacist, so she has been dealing with this type of questions for years in her professional life. Marian was a PhD student in, how do you call your field? Like neuroscience? Yeah, neuropsychology, yeah. And Manali was a software developer. So this is what happens when you combine very diverse backgrounds to go for a project that sounds technically very challenging. But as you can see, it's immediately useful to a person, in this case, a pharmacist, right? All right, so there was one question on the chat that we haven't addressed yet, which is a technical question, so don't run away too far. Why is there variance when you ask the same question multiple times to the model? Okay, let me repeat the question. Why do you get different answers when you run the same question multiple times? Why is there variance in the model? Yeah. So the same question, multiple answers, right?
So it depends on how we do the decoding. So we selected the temperature to flatten the probability distribution, and that would result in more creativity of the model. And since GPT-3 has been trained on this huge amount of data, it has so many data that every time that it changes the probability, the output is still valid. So if we do that for a smaller model, then the output is not that good. When it gets more creative, it gets less factful. But for GPT-3, getting more creative is still in the limit of being factful.
So and you can control the variability.
Yes, through the decoding method. And that's why for GPT-2, every time we run it, we get the same answer almost, because we set the parameters so that we get the same. It gives us the same answer because that's more factful.
Okay, that could be an issue for a company running this commercially, right? They may have reproducibility, right? So it could be that having the same answer always benefits the company.
That is possible through the temperature parameter.
Yeah, when you set the temperature too low, you receive always the same answer, but when it's like not factful and just wrong, there's no chance to have the variability and see another answer. So in our use case that we have in mind, like using this as text generating and having ideas how to answer, more variability is quite a good thing, because we have the filter of a domain expert that filters the answers of the model before a patient sees it.
Right. So I think I know the answer to this question, but I'm going to ask anyway. Is there any way to include feedback? So if an answer is bad, me as a user, can I mark it as a bad answer, and then you will help with the future answering?
At the moment, not, but that would be quite useful to make the model and the answers better. Yeah.
All right. So I think we are good to go for our next team. Oscar and Jacob, they are both ex-academics with PhDs in physics and kind of super mathy stuff. They're going to do signal processing, sound-related topics because they both care about music, and they were interested in doing things with music. They're both actually C++ programmers, so they could potentially implement this as a plugin in an actual DAW, music production system. So the project is about whether you can remove reverb using machine learning. Okay. Okay, so we are really adamant on not changing computers during presentations because things like this could happen. But there is always somebody who has something on their computer that they cannot really run outside of it. And this was the case with this project that has audio files and so on. So we unplugged a new computer, and you know how technology is. When you're live, always something is going to happen. Mostly every project has a live demo, and the live demo effect is that it doesn't work when you are trying to demonstrate it to the public, right? So far, the demo with the pharmacist type of questions worked quite well live. So let's hope that the trend continues. So now we are trying to open the slides on the new computer. So it's not like we are solving like rocket science here, right? So this could be a joke, like one of these, like how many theoretical physicists do you need to screw up a light bulb, right? So this will be how many theoretical or experimental physicists do you need to get Google Slides on the screen? And now high expectations, everything is running on this bed. Do we have a screen? Okay, so now the projector seems to be not liking the new resolution. Yeah. Igor says use a whiteboard. And this is why we don't do the changing, right? Okay, so now we seem to have X a crash, so X or crash. So we have a terminal right now showing characters. Okay, what we are going to do is the next team is going to present while you guys figure out what's happening, maybe reboot. Let me see who the next team is. Karim, can you present? Okay, so the next team is in the bathroom. So okay, then we go to the next team, which is Evelina. Okay, just take. Frank, can you get the computer from noise? Okay, so now we are back on programming, skipping two projects because one of them is in the bathroom. Okay, so now we are going to go to a project that is kind of a sensitive topic, right? I wonder how many people in the audience have done a PhD or tried to do a PhD and what your experience have been. But from my 8 years at DSR, I've met plenty of PhD people. I did a PhD myself, and many people report that their experience is really tough. And this is something that it's an issue. People, universities know this, that mental health is a problem. People are really quitting without finishing their PhDs. Those who finish their PhDs don't have exceptionally good labor options. And we were wondering whether you can use machine learning or basically simple statistics to decide where to go for a PhD or whether your career as an academic is going on the right track or not compared to other people. So this is what Evelina did. So let me get you Evelina on a new computer.
Thank you. So yeah, my name is Evelina Zakharieva, and I'm going to show you a database which helps to visualize the outcome of PhD research in Germany in terms of publications of scientific papers. So let me explain why why I decided that this is important and why can it be helpful. So in Germany, not only, this is not necessarily working. Okay, I switched by hand. Yeah, I switch it from here. So many young and talented people decided after the master program to stay kind of in academia, to continue and become real scientists doing a PhD. And this is indeed very exciting think option, and many smart people want to do it. They want to become real scientists. And then also you can find in internet very many options how you actually find your dream topic. You can be prepared for what you want to do, what you can do your research. There are many hints how you find the topic you actually really want to spend 3 years of your life doing research and contributing to the knowledge of our society. Yeah, for example, this is the page of the Federal Ministry of Education and Research, where you read that roughly 29,000 graduate students complete a doctorate in Germany every year, which is above the average in Europe, in fact. And there are many nice search engines, for example, the database of DAD, where you can explore what are the open positions and really find your dream place. And if you are lucky, you can also get it and start working on it. But what often happens is, let's say, after the first year, things are not as ideal as everybody was imagining from the beginning. although you are smart, you are talented, you really work hard, it really happens that you get stuck at some point. And there might be very different reasons for that. For example, your experiment is not working, or it's not reproducible, or the results you are getting are not the ones which were expected, or you don't have enough support to evaluate data, or whatever. Or you maybe even don't know why your boss is asking you to do this again and again, because these are very, you work many hours on something and you expect that it works. But okay, sometimes, often, it's not exactly the case. And many of these young people actually experience the effects of burnout, depression, sleeplessness, headaches, and all possible things in this regime. And the nice thing, the good thing is actually now there are people and organizations that start to talk about it. Because until recently, it was not very much discussed. It's assumed that it's a personal problem, it's just bad constellations of circumstances. But if you look, for example, at the webpage of Scholar Minds, which is a mental health network for Berlin scholars, you may read already on the homepage that according to Max Planck PhD net study, 53% of the PhD students are affected by this. And actually, I was working a very long time, about 10 years, as a coordinator in a graduate school beside of my scientific career. And I can tell you that there are many places where actually the percentage is clearly higher than 53. And it's not easy to answer the question how you can, why this happens. There are many reasons behind that. But one interesting question is, okay, what could help? What these people need in order to not experience the feeling of failing, but what would give the feeling of being successful? And actually in academia, these are the publications. You need to publish your result. You need to show it. At the moment when it gets accepted and you see your publication, then you see that somebody else cares about you and about what are you doing. And in fact, in science, there is something called publish or perish. If you are not working in academia, maybe you Google it and then you can read that this is an aphorism describing the pressure to publish academic work in order to succeed in academic career. But it's not only this. In fact, everyone working in it, especially in an early stage career, like a PhD student, need to see the work published, because this actually means that all the hours you have spent in the lab or behind of your computer matter for somebody else, or they drive the science a bit further. And that's the reason that actually many students or many people working in academia would spend, let's say, Christmas Eve behind a computer trying to really finish the publication and submit it, because the boss, but also you, really want to get it done before the end of the year. And this means you ignore your family, you ignore nice holidays in order to achieve this. But then the question which is really asked at that stage is, okay, how many publications are actually published per PhD thesis, like in this 3-year period? And what you could do, or maybe will think of doing, is ask Google about this. So how many actually are published? And then you get these 3 publications. Okay, but is it the real answer? And then if you read, it's saying, in my opinion, every PhD candidate should aim at producing at least 3. But it doesn't mean that it happens. And if you read further, this is an answer to a question, what is the percent of PhD students in a university who publish 2 or more in a journal with impact factor at least 3? And then here it's also saying, I hope universities collect data on their students who publish in peer-reviewed journals. And my question is then how many? So it's kind of a hope. And then if you read further, for example, in this site, Find a PhD, which provides very useful links to the field, you find the first question here. Just wondering how many publications people tend to get during their PhD. I have just finished my first year and I feel like I'm the only one who has nothing in the pipeline. So what I want to show is that actually there is no answer to that. It's really surprising, but it's not known. You may ask, you may look around, you may feel something. There are strict rules that you maybe need 3 or 4, this depends on the institute, but actually how many are realized, it's not that easy to answer. And that was my motivation to try to answer this question using the tools of data science. So how this question can be addressed? Of course, the first thing is to find information about how many PhDs are completed in Germany for given period. And the obvious place where you can gather this information is the German National Library, where they collect information about every PhD. And it's a very nicely structured site where you can search and you find about, actually, I was downloading the information for the last 10 years in the fields of natural sciences and mathematics, as well technology, medicines, and healthcare. And these are about 250,000 records. The data is very nicely structured. You have title and so on. There are actually fields, which this Sachgruppen. And these are very nice because they are predefined. The problem here is only the university, which everybody could write the way he or she wants. And this requires a lot of data cleaning. And it is time consuming to download it. In fact, it took about a week web scraping at this page, but otherwise this was the easier part of the project. Then surprisingly to me, in fact, was that it's more difficult to find out how many papers are published by these people. Why I was surprised that it's difficult to find it out? Because actually publication is, scientists actually need to pay sometimes in order that their works is published. They don't get money for that. And this is supposed to be available, at least the information of what has been published is not the publication on it itself. But if you ask Google Scholar for publications, what you get are answers like this, like there is no complete author list, the journal is also not given completely, and so on. And in fact, okay, that's Google Scholar. There are other APIs like Scopus and so on, but they're not free of charge. You actually need to pay in order to get information. And in addition, it's time consuming. It's not fast, as I mentioned for the German library. And it's not straightforward. You still need to write this code besides of paying. So, okay, it took me a very long time. Actually, more than half of the work on this project was collecting this data. I managed for 2 years only. And that's what is implemented now. And I combined the data from the German library, from the publications for 2 years, and impact factors of journals from this site to build a web application. That's the QR code for the web application. Actually, for the moment, it's still working. The server, the database is on my computer, so it will work properly, most likely only during this event. But it's still something that can be tested. And this is how it looks like. You may go to the search button, and then you find how many, actually, where are the places where one can do a PhD, and some statistics. How I decided to organize it, I plot the institutes, and then the total number of PhDs accomplished here. And you see the same list on the right-hand side. You can click at the universities. Then on the next plots, the order of universities is the same. It's always universities on the x-axis, but here is shown the total numbers of publications. So I get about 43,000 people with about 150,000 publications. So in a way it fits. You may divide the two numbers. It's about 3.6 publications per PhD student, which is in line with the requirements. But then, not all of them are before the PhD. And also, it's a question in how many are you a first author? And how many of these are published before the PhD is completed, and so on. In science, actually, it's important if the journal has an impact factor, because many of these publications are published in archive and so on. So the question is how many publications you actually get in journals that count in terms of being impactful. The measure in science in this for this is the impact factor of the journal. So you aim at publishing it in journals with, let's say, impact factor above 3. So if you scroll down to the last plots that presents this information, you end up with a total number of about 0.4 per student, meaning even not every second get a publication in such a journal before the completion of the PhD. And this is in average. I mean, you can filter here. For example, if we look at chemistry, where people tend to publish easier in a nicer journals, I mean, more cited journals, then this number goes to 0.9. Almost everyone gets a work published. But what these numbers tell you, why this may change anything? The point is, okay, that's what you may think, may hope you will achieve. So don't aim at too much. For example, I'm not saying it's okay if you spend your Christmas Eve trying to publish your paper, but if you spend 3 years the Christmas Eve hurrying up to submit your paper and you still don't have anything published, then maybe that's a warning sign that tells you, okay, here there is a problem and that's not me. Or definitely there is something else which contributes. It cannot be you are rushed really every year that you should submit and then nothing happens. And you are also maybe not that likely, depending on the place, to get these 3 publications that easily. So that should not at least be a reason for being depressed and so on. And it's good to know this in advance before starting the PhD, in order to avoid having too big expectations about the story. So that's what is your actual contribution, your actual impact at the end, an average. That's how it is simply. So what can be done further on this application? Of course, more sophisticated filters. What I was planning to implement didn't manage, did not have the time, was to have search. Nowadays, a search engine, like you may type a keyword and the app will search through the titles of the PhDs and gives you statistics about the titles that contain what you have written, but there is no context in this. I was planning to use word embeddings and so on, but did not have the time to do it. The database could be extended to more than 2 years, and it's nice to cover individual research groups, because what is shown now is averaged per university, but this does not reflect really the situation in the individual groups. What is interesting and still missing, and very important, is to have an estimate about an average duration of a PhD. So how long does it take to have this paper published? In theory, it's 3 years, maybe 4. In practical terms, it's actually much longer in many cases. And these cases are not that small percentage. And even more important, how about the not completed PhDs? Many people start but never finish. And then they're just out of the system. They're out of the webpage of the university, they're out of the statistics. You simply don't know anything about them, and they leave the academia being completely desperate, spending 3 or 4 or more years on their life, having no PhD, having nothing to prove what they have been actually doing during this time. And they're not even part of the statistics. And this information every university has, but it's not publicly available. That's a problem that cannot be solved only with the tools of the data science. So I want to thank Jose, who was my mentor in this project and who is actually organizing this school. And so maybe that's the moment to mention that for people still being in academia after the PhD, this place is really a great opportunity to get out of the university, because what we got here during these 3 months is exactly this introduction about what is happening in the field right now, what are the recent developments in algorithms and best practice in data science that would actually really help transitioning from academia for people who have been doing this somehow, anyhow, in order to get it to know how it's actually working in industry and what is the state today. So I'm very happy to have the opportunity to be part of this school. Thank you, Jose, and everyone else from this class.
Okay, so it's time for questions. If you have any on the chat or in the room, you can ask now. I want to say something about this project because it could look kind of dry, like, oh, numbers and bars showing me how many PhDs people have in Germany or how many papers they published. So what, right? So let me tell you the so what from my point of view, right? So it turns out that people pursuing PhDs tend to be smart, let's say on the higher end of the scale in any society, right? Germany has the highest number of PhD per capita in Europe, perhaps in the world, right? And what happens to these smart and highly motivated, hardworking people, right? So 53% of them get depression, anxiety, problems sleeping, all the things that you don't want to have, right? And those are the ones who actually push it through and finish. Many of them, we don't have the numbers because this is a big hole in the data set, right? They don't finish. And what happens when you have half a PhD? Well, you have nothing, right? Your chances to get a job don't increase because you have half a PhD. And well, let's say that you are doing well and you got your 3 publications, and then everybody thinks that you are racing the star in academia, right? Okay, what happens to you? Then you are destined to work 7 days per week, 12 hours per day. This may or may not be an exaggeration because we all know people who did that. I did that. And your chances of being a professor are between 1% and 3%, depending on the topic, right? These are very dark numbers, right? Would you risk your mental health for a 1% to 3% chance to be a professor? And it's not like professors have an easy life and then they just goes through. This is a serious societal problem. We have people who are really smart, who don't get any benefit from their work. And the power structure is such that a professor that has already a lab running, or it doesn't have to be a professor, a principal investigator, can take advantage of the work of many people who don't know better. And the reasons that we don't know better is that we don't have data. So this project was aiming to answer the question of, okay, I'm 5 years in or 6 years in, I've done 2 postdocs. What are my chances of having a good life inside academia? These are questions that your university should answer, but I don't think it's being answered right now. And I would have loved somebody to give me data, hard data like we have here, this project, to answer this question myself 50 years ago or so when I was a PhD student, right? This didn't happen. So this is what we are trying to build, right? It's not only that, I think people should support each other because it's very unpleasant to be alone when you're in academia and everybody has the mindset of publish, publish, publish. I want to be a professor, right? If you say, well, what if I don't want to be a professor? What are my options? You are an outsider immediately. And I think this should not happen. So I created a community together with a bunch of people here, Evelina included, so that people will talk more to each other who are going through this process. So I want to reach those people who are feeling the burn of academia before they burn out completely, and tell them that they are not alone, that there are more people and they can talk to each other. They can go to events where somebody who made a successful transition can speak about their experience. And that community is called unstuckphd.com. It's not live yet. It's kind of getting there. I hope to get it finished by today, but I couldn't. There will be an event next Thursday, not this Thursday, but 2 Thursdays from now. If you want to join that community, join that event. I'll post the link on Twitter and LinkedIn and so on. And now we finally have the computer working. So Jacob, yes, is yeah, Oscar and Jacob are apparently ready to go live. All right. So this is the project that I was telling you about with removing reverb from audio, which is a very tough task and very valuable for anybody doing music production or even facing problems with audio in a Zoom call, right?
Okay. Yeah, our project is about removing reverb from sound. I'm Jakob. This is Oscar. Sorry for the mess before. So what is reverb? Just imagine you have a room like that with one person standing on a stage, talking to another person in the audience. And then there's one way the sound could take. It's just a direct path. It's called a dry sound. And that's the sound without reverb. It might sound something like this. There's no reverb at all, but sound is not like just not like this. Oh. Okay, now this is not the only sound which arrives at the person in the audience, but you also have the sound which is reflected from the walls, and the reverb is just the sum of all the echoes reflected from the walls, and then this might sound something like this. So sounds very different. Our task is to remove sound reverb from sound, which means we start with something from the last sound example where we have a lot of reverb, and we want to end up with something where we don't have any reverb. So what are possible applications for this? First is speech transfer. Everybody has experienced that in a Zoom call, Skype call, or phone call. We have some reverb. And another possible application is music production. Typically in professional music productions, you record the sound in the studio where you have as few reverb as possible, and then you add reverb artificially in post-processing. That's the standard procedure in music production. So the tasks are a little bit different. So for the first task for speech transfer, it requires real-time sound processing, while for the second task in music production, you do not really need real-time processing, but you can actually do it in post-processing. And generally for speech transfer, the sound quality doesn't need to be that good. But for professional music production, you of course need a very high sound quality. So our task is to remove reverb from sound, but it's very instructive to understand how you actually add reverb to sound. So this can be done mathematically by a convolution. The convolution is shown as this mathematical formula on the right. It's quite a simple thing to do. Actually, so what you start with is anechoic sound, which is sound recorded in a quiet chamber or anechoic chamber. You see a picture of that down here. It's a special chamber which absorbs all the sound from the walls, such that you don't have any reflections. And that might sound something like this. And then you do convolution with a so-called impulse response function. How does that sound? The impulse response function. Let's wait it again. It's just a very short sound. You can record that, for example, by clapping your hands inside the room, and then you record the response from that clap. And this completely characterizes your room acoustics. And that's called an impulse response function. And it's really synonymous with reverb. Different reverbs correspond to different impulse response functions. And that's actually what we want to remove from the sound. So the impulse response function depends on really many things. It depends on the room size and the room shape. It depends on the position of the source and the receiver. And it depends on shapes and sizes of objects in the room. Everybody has experienced that if you go into an empty room, the reverb is very different, the sound is very different than in a room which is full of obstacles with furniture and so on. So what are the strategies for reverberation to remove reverb from sound? We can distinguish two different strategies here. In one case, this impulse response function is known, which basically means you know the reverb, you know where the sound is recorded, you know the room acoustics. And then you can deconvolve the signal with the impulse response function. That's just mathematically just the inverse operation of a convolution. And it's mathematically not very simple to do, but it's well known how to do that. And this task does not require any neural network. The really hard task then is if the impulse response is unknown. So just imagine if you do a Zoom call or a phone call, you do that in a place where you don't know beforehand in which room it takes place. You don't know the room acoustics, you don't know the reverb, So the impulse response is unknown, and still you want to remove that somehow from the sound. And this is a task which can be done or can be tackled by neural networks. So then we thought about two different strategies to do that task. The first is to classify the unknown impulse responses with a neural network and then deconvolve with a known impulse response. I will explain that a bit more in detail on the next slide. And the other approach is to predict the dereverberated signal directly with an autoencoder. Oscar will tell you more about that. So the first strategy we tried is dereverberation by classification. It works as follows. You collect this set of known impulse responses. From that, you generate your sound with reverb. Then you train a neural network for this impulse response classification, which means now this network can really recognize the kind of reverb you have in your sound. And then you apply this neural network to sound with an unknown impulse response. And to classify that means something like you determine the known impulse response function, which is most similar to the unknown impulse response function. And then actually you do a deconvolution or with a known response function, or you take a linear combination of known response functions and you deconvolve your sound with reverb. So we tried that approach. It works okay with a small sets of impulse responses, but it's not that well. You actually, to make it work really well with a good sound quality, you would require a huge set of impulse response functions, and we are not really able to do that because you need big resources for that. Yeah, and the next part is about different autoencoders we tried.
So yes, one of the reasons we took this project with audio is because we are music and audio enthusiasts. And also because almost no one is doing it. And why no one is doing it is actually because it's really, really hard. So why is it hard? We have an audio signal, and the audio signal, the quality that we are used to requires at least 41,000 samples per second. This is a lot, and we cannot input such long vectors to regular neural networks, so a dense layer wouldn't work on that. So to work with audio for ML projects or neural network projects, we would need to compress the information to reduce the dimensions somehow. One way of doing it is to use short-time Fourier transforms, which will give us some spectrograms, which consists of complex numbers. So we have a frequency distribution in time, but represented as imaginary and real part. So we can reduce it further, taking a magnitude and logarithm and scaling a little bit the spectrogram, which is called a ML spectrogram. Then we get rid of the imaginary part of complex numbers, and this is great. However, we cannot go back from the ML spectrogram to STFT and back to audio. And this is a huge problem. It can be solved by some algorithms which have bad quality, or we can use neural networks that were already developed and deployed. But on the other hand, those are very slow. So we have some possible strategies to work with our problem of removing reverb. We essentially need to use some kind of autoencoder or autoregressive method, and autoencoder is architecture here, where we take as an input some sequence. We try to reduce representation of the sequence while having as much of a valuable information as possible. So then this compressed information will be decoded by a decoder to something that should be essentially the same or very, very similar to what we inputted, but without noise, maybe, if it's trained the network to do it without noise. In our case, we would like to have the output signal without reverb. So there are a few ways to go here. The most common is to work with ML spectrograms. So we can use autoencoder and then use something that can decode the ML spectrogram back to the audio like Waveglow, but this is too slow for real-time execution on CPUs. we could use wavegun, but it is still slow. Then we can work directly on audio signal, and we've tried that with autoregressive models. So for example, LSTM gave us a very bad quality. Then we tried WaveNet, which is essentially 1D convolutions with some dilations, the special one, causal. And those are very slow converging. And also they gave us no reasonable results, no convergence at all wherever we tried. Then we have our own idea to use a wavegun, pre-trained wavegun. However, we wanted to use transfer learning to teach it to omit the reverb in translation. So only translate speech back to the audio and leave the reverb out. The last way we tried is to use directly STFTs, and this is something that almost no one does because it is thought that neural networks cannot deal with complex numbers and they get lost there. But first we need a data set. So we used the anechoic data set, as Jakobs told us. However, we cannot use the whole data set with our all reverbs because we have somewhere 40,000 samples. And if you want to add 2,000 reverbs to every sample, the data set would be way too large. So we used data augmentation on the fly. And we have some target audio. Oh, damn. And so we have some target audio in Czech language, of course, because it's great. We add some reverb on the fly, and we want back the target audio. We also take different frames in time from our data set. So every time it's a little bit different signal, a little bit different sample. We take convolved signal and we add them together back with different proportions, which is supposed to simulate how close we are to the microphone. If we are close, then there is more of the original signal. If it's far, there's a lot of reflection there. And that was the idea here. But this makes our training to be very, very slow. I mean, not very, very slow, just slower than normal. So first, we tried this Melgan architecture that is actually very good in translating the MEL spectrograms into audio. Let's see some example of a trained Melgan. So this would be speaker that the network has never, ever seen.
Corporate banking would be based in Edinburgh.
And now the translation.
Corporate banking would be based in Edinburgh.
So I don't hear any difference, so I think it's very good. So now we try to train it by ourselves, and it sounds somehow like this. This is input audio.
Printing in the only set.
This is our output from the network now. Yes, so after 600 or even 700 epochs, we didn't train it. Later, I found that you need at least 1,000 more epochs, and it would take somewhere 14 days on one GPU. So yeah, we didn't do it. Although still, I think it is the most promising architecture to actually remove reverb and have a good quality. Then we tried something that could work really fast in real time on a CPU. So we tried to the regular vision autoencoder, which has as an input a MEL spectrogram, and as an output we want STFT. So both real and imaginary numbers are to be predicted. Then we want to do inverse STFT and get back the audio. So this sounds like that. First, I will give you the input, then output, and then how it should sound. Now the output of the network. And it should be the last sound. So not very good, of course, but that was, we knew that it's gonna work like that because not a lot of people try this. So our last idea was to use only STFT spectrograms. So STFT spectrogram is going in, as an input and output from the network. However, this time we also take a residual connections. So the input STFT will be element-wise multiplied with the output of the network. And here we wanted network to learn some operation that when you multiply it with the input complex number representing audio, that this operation could maybe remove some of the reverb. Let's see how does this work. So first we have our input audio with reverb. It will be only very short reverb. Now the output of the network. And how it should sound. So we can see that it's not too bad. Let's see. Actually, I did it remove reverb because it was short. It wasn't really obvious whether it does that. So in the slide, in the image A, we have input audio with reverb as blue and prediction, so the output of our network as orange. And we can see that blue signal has some reverb in between the words, and that our prediction does not have this reverb. On the slide B, we have a target as blue and prediction as orange. So it's close to the target, but not exactly what we want. As you could hear, there is too much of the signal cut from the voice, so the output signal is not as good as we wanted it to be. So again, Melga did not converge. Mel2 STFT did not produce reverb, but also no reasonable sound. And STFT, it's a proof of concept for us that you can work with audio with STFTs, which is very important because I don't think much people thought about it. And we think that maybe not for reverb, but for some other applications, it could work. So our conclusions are, in general, that we didn't have enough of reverb. 2,500 examples of reverb is not enough to sample the space of reverbs well enough for any of our applications, actually, to predict a reverb or to deconvolve it. The reverberation often leads to some distortions of noise, and therefore we should probably use several architectures or maybe some kind of digital signal processing filters, because there's a lot of them. And our outlook expectations for this project was actually not to remove reverb because we knew it's very, very hard. The convolution operation is not easy to revert. However, if it would work, it would be super great because it's not only reverb that you want to deconvolve. This microphone and all the audio equipment has its own impulse response also. And in the audio applications, you would sometimes want to get rid of the distortion that your microphone does to your signal. So that didn't work, but I think that the STFT network, when we work with complex numbers, could be way better to removing unwanted sounds like harsh or resonating frequencies on recordings, or noise, tape, hiss, clicks, and pops. Or also when we have recording in church, for example, great concert, and then there is someone coughing or children crying, or you hear some urban sounds on the recording. I think that the STFT might be even good at this kind of applications. Thank you very much. Now some time for questions.
So any questions? So in my experience in music production, basically, sometimes you want to sample a sound, like imagine that you like the sound, for example, of somebody stepping, but you cannot just go and record it and use it immediately because it has all kind of unwanted things, mostly reverb, and there is no solution in the market to remove reverb. And this is such an obvious problem. But okay, let's go back to more pedestrian things, day-to-day things. In Zoom calls, you often have Peter who has some really bad sound, right? And it's kind of a problem that, I mean, during Corona, everybody made what they could with their setup. Rarely people buy good microphones, so they are in their kitchen or their bedroom with a poor microphone. They have to make it work so that the audio quality is decent. But often in a call, there is somebody with background noise, with a poor microphone, with some problem that would be wonderful that you could remove that by just pressing a button, right? So this type of programming that Jacob and Oscar are doing is aiming in that direction. What happens if you could process the audio and remove the unwanted parts so the quality is higher? So when you actually play the results of the network, most of the results that you've seen sound kind of scary and weird, right? But that's not the point. The point is that eventually you can get a system that gets you the results that you want. So imagine the button to make Peter sound better. And we have a question. Okay. So somebody from the audience is coming to the stage to ask the question, like in olden times.
Hi. Actually, I have a question. As far as I got, you were aiming to run the system live so that the delays in time should be small. That it could be live system, yeah, right? What if you would have unlimited power, and what would change this in your project? Would you select a little different strategy, go to bigger networks and no so these connections with the multiplication, or?
Thank you. That's a very good question. If we have unlimited power, or if we know that music producers started using GPUs, we would use a wave-glow network, which is the best with translating MEL spectrograms to audio, and we would work only on MEL spectrograms, which we didn't do because we really wanted real-time CPU application for maybe our future projects. Maybe some other questions? Are there?
All right. So, guys, we are finally going to get the hardest to get team so far. Applying data science to telecommunication networks by Karin and Naveen. So, Karin. So if you ever wondered how the internet works, you're going to get somewhat of an explanation here. And they're using reinforcement learning. So these are two difficult topics, and it's a very dense presentation, just so you know. Just brace yourselves.
All right, we'll make it. Hello, everyone. So today we'll present to you our project, which is internet traffic optimization using reinforcement learning. So we'll start with the motive of the project and talk about how we approached it and present the results. We have a clicker. So let's first talk about the current state of the internet. So the internet has revolutionized our life. It has basically shaped what we do over the last 20 years. It's a very important aspect in our lives. And clearly there's as you can see, there's a direct correlation between developed countries and internet use. But traffic is increasing at an exponential rate, which is not surprising, but it's putting a strain on the network and increasing congestion. Although the speed is increasing, because how we approach the problem until now is by just adding capacity. So physically improving our networks more and more. However, the exponential increase of traffic and also with the change in format of what is being sent on the internet. So when we used to do text and images, now we're sending high definition content, 4K. So it's increasing in size and volume, and the format is also like putting a strain on it. So keeping up with the same solution, which is adding more and more capacity, is going to be exponentially costly because traffic is also going to increase exponentially. And it's unable to keep up with the actual increase in traffic. There's actually a physical limit to how much you can actually put and in terms of links. So we need to think about how to solve this in a different way. I'm not saying we should drop the solution of increasing capacity, but we should combine it with a different one to make the internet more efficient. And so we need basically a smarter network to work along with the evolution of the physical network. And so what is the internet? The internet is basically a connection of subnetworks. We, the end users, send stuff. We are connected to a local area network, and the messages travels up, and from the regional local internet service providers to the regional one, all up to the internet's backbone, which is consisted of a wide area network, which connects. Basically, this is where we share the resources with everybody who uses the internet. It is then routed to the correct exit, which is connected to the local area network of the receiver, and then it travels down up until it reaches the receiver. So we could make an analogy of the internet with actually regular traffic. The cities are actually connected by highways, and inside the cities you have small streets. So whenever you want to travel to a different city, you actually need to take the exit that's actually closer to the next city and route, and so take the steps which will get you closer to the next city. How it works with the internet is basically, so you send a message, the message gets segmented into packets, and then each packet is sent and reassembled at the destination. So whenever there's high traffic, there's high congestion, there's a higher latency to the message, so reliability is decreased. What you can do with regular traffic whenever there's high congestion is basically take a detour and take a road that is less congested. But this might not be very efficient. It might not be a good choice because like you would actually have to travel longer physically and like put more time, and when you could have sat in traffic and waiting. But with internet and packets, because they're electrical signals, it might be very logical to actually send it far away and route it through a different way back to the destination and avoid having this passing through the congested traffic. And so doing so will enable us to actually reduce congestion points, distribute the traffic all around the network, and so basically make use of the distributed computing system that is the internet to actually have a more reliable, more efficient service. And it actually doesn't cost that much because basically it's just software. So you'll have just to change software instead of like building stuff and having an increase in cost. And so what can we do to route the packets differently? And what we try to do basically is apply reinforcement learning. So so I have an agent look at a network and decide how traffic should be routed, like for every hop until it reaches its destination. So for doing reinforcement learning, we needed the four stuff, which was the environment, a traffic generation, an agent, and a neural network. So for the environment, before deciding how to build it, we first have to ask ourselves, what kind of network do we want to simulate? And so is it a local area network? Is it a wide area network? What kind of communication links are we using? Are we using a one-way communication link or a two-way communication link? There's actually also different topologies, mesh, three, ring, and star. And so in order to make our decision, we actually research where congestion is mostly a problem. And it's definitely where we share the most resources, which is a wide area network. A wide area network consists of a mesh, kind of a mesh topology, and it has a two-way communication link. So a router can send at the same time as it is receiving. And so yeah, basically, and with that, we started building our environment. And okay, so this is the network that we use. It's basically made out of 5 nodes. You can visualize the nodes as being cities, and the actual links as being like the highways connecting the cities. Each node has a queue size where the messages are actually queued until they are processed and routed to the next destination. And apart from that, so we have different actions available based on how many links you've connected to. So basically, node 1 is connected to 2 links. It has 2 actions, and there's also the action with 0, which is do nothing. And so whenever a packet is routed, if it reaches the destination, it actually disappears from the environment because then it travels down. So basically, if we wanted to go to Berlin and we reach Berlin, then we go inside Berlin and go to wherever we want there. So we're not in the network of highways. And we get basically a positive reward because we reach our destination. Whenever it is routed somewhere else, well, depending on the queue occupancy, because we want to actually favor less congested queues, we assign a negative reward, which is minus, so the next queue occupancy. And finally, the reward of -0 is assigned whenever we're taking an action 0 and there's still packets that needs to be sent and queued. So basically, our environment looks kind of like this, which is a multi-discrete action. So you're taking 5 actions every time. Each action there's 4 options per actions, 3 for node 1 because it has 2 connections, and our state is modelized by a 2D network with a 5 by 10. 10 because we decided to have a queue size of 10, and 5 because we have 5 queues. So to make it better visually, or we first have to talk about traffic generator first. So the traffic generator, we have 5 waiting queues for each node. So each node so for each node, there's a incoming traffic. And so these are called waiting queues basically, and they have different rates. So these rates basically define how busy the traffic is in this node. And we could simulate a stable traffic with every node having the same range, having the same rate, or we could actually congest a region or congest a specific node and observe how our model changes. So whenever the incoming traffic arrives, if there is space, the packet is actually added to the bottom. Because it's like this is how it should be. Whenever it is routed, it's added to the top because we want to prioritize the delivery of the earlier packets, so not having them run through our network endlessly. And whenever there's no size in the queue, we have a dropped packet. And so we have this metric that basically gives us an information of how reliable the network is. So putting it all together, to make it visually understandable, let's say that you have 5 nodes, 5 colors. The roads are actually the access to the nodes, and so basically the traffic generator makes use of the roads, and the roads are also used to route the packets to the lands whenever they are delivered to the right node and back. So in here we have on the left the current state, which consists of the queued cars, which have the colors based on their destination. So the action we're taking an action, and then we have a new state. So the blue car on the bottom is queued in the queue of the yellow one to indicate that basically there's incoming traffic. Because as we can see, we're taking 2 red actions, and these actions are for node 5 and 2, and so they have at the top red cars. So 2 red cars are routed to the correct location, and they leave basically the environment. And apart from that, basically this is how the routing works. And it's basically, this is just a theoretical explanation. What is actually happening is there's like lots of more movements of packets and cars and whatever. So Naveen is going to talk now about the agent.
Yeah. Thanks, Karim, and hi everybody. So I'll be looking at yeah, agent part and a deep neural network part. So here I'll be explaining why we have selected this kind our agent and why we have selected our neural network. So before that, I'll be yeah bit of about reinforcement learning algorithm. So and it basically it can be divided into two types. One is a model based and one is like a model free. And yeah, in model based, it determines its own path. So we give basically first like a path and it takes the directly actions. In model free, it is other way around. And under model free, we have two types. One is a policy optimization and another is like a Q learning. And in model based, we have like a learn the model and a given the model. So yeah, so in our case, we have selected actor critic algorithm by doing a lot of research, and so in our case we have like yeah, we have 5 actions, and each action has like 4 steps. And here in actor critic method, what exactly actor does? So actor is like it creates its own policy and by taking critic reviews. So critic gives the value and it gives the feedback to the actor, and then actor takes this uh, action and action goes to the environment. Then environment will give back to reward and new state. From there we can calculate advantage function. So once we get advantage function, by using advantage function, we can calculate gradient. So we take these values to feed this our neural network. In our case, we have selected convolutional neural network, and it's very good in yeah. So yeah, so it's very good in giving uh, extracting features. So in our case, we have 3D space. So it takes the 3D space and gives to convolution layer. Then it goes to the pooling layer and then does flat. So from flattening to, so it goes to a fully connected layer and we get our results. So in our case, we use 2 convolution layers and 2 fully connected layers. And so once we feed this before feeding this, we have to do a bit of pre-processing. So in our case, we have 2D space. So we have to convert 2D space to 3D space. So how we did this one? By using one hot encoding. So once we got this 3D space and we feed this value to our network and we got our output. So we got total 10 outputs. In these 10 outputs, we have 5 actors, and we can see here in picture in 5 actors, we have total 4 steps, and we also got 5 credit. So this is how we got our results. And next, Karim will be handling about results and conclusion parts.
So yeah, basically our agent was the actor critic because basically we did not have a policy. We don't know what strategy to use. So we wanted our model to come up with its own strategy. So we wanted to have some kind of policy optimization algorithm. But on top of that, we also, because we have a huge action space with like 5 actions and 4 possibilities for each action, which is basically why our actor layer looks like this. It will be very inefficient of just having a simple policy optimization. And plus, we really needed to have some more information about the state, whether it's congested or not. So basically, the critic, which evaluates which is also a part of the network, it evaluates the state. So combining both, we're able to train it better. And this is why basically the actor critic works well technically. So as for training results, we first trained our first model, and it was basically with a different routing penalty. So we were assigning -5 instead of the next queue occupancy. And what we found out is that basically after running multiple episodes, it stuck to one loop. So basically the red one, which, and so it's constant action, which lets all packets travel around the network. So basically everything will be delivered at one point, but obviously it's not the optimal path. And whenever because basically this training was, we did not have the traffic generator in it. So it was the first one. So whenever we will add the traffic generator, things won't work as well with this, and we will have dropped packets. And yeah, and as you can see, that like the variance basically stops changing for the score at the end, because it sticks to this move, and this move basically yields like the same results technically. So our second model, which is including the next queue occupancy as a penalty, and doing that enabled us to basically get better results. So in here, we're looking at average of the average running scores, basically to be able to figure out the trend, because it was very like the variance is very high whenever the training is happening. On the left, we have a random baseline, which technically sticks around between like the less than -1,000 as a score. But on the right, we can clearly see that our agent is becoming better, and like over time, and we're training it with 3,000 episodes, which is not much, but like using the computing resources that we have, it took like 3 hours at least. And yeah, apart from the score, we also measured the runtime, which means in how many steps an episode is completed. And the same thing is happening over here. So the runtime is increasing, which means that our agents are becoming smarter, taking better moves, and basically ending the episode faster. And because we don't have a traffic generator, we're just ending the episode whenever all the queues are empty. Yeah. So there's actually great promise in implementing reinforcement learning to a network. As we can see, it's improved, like it learned a lot, and it's basically with like very little resources. So with more and more training, things can be better. And the next steps would be to plugging in the traffic generator, which is very important for us to simulate real life events. And that's for actually deployability. Additionally, it could help us test for latency and dropped packets, as whenever packets cannot be queued into the nodes, they will be dropped. So it will help. We will have like this metric, which will indicate information on the reliability of our network, and the order of delivery of the packets, which can put a strain on the receiver. That also can be measured. We will also need to increase our queue size and network to simulate a real wide area network. And what we can do actually is use the core emulator, which is basically an emulator, like it differs from a simulation, being that it actually collects the real data from the real networks, and we could use these to see how our network will perform on real world data without having to worry about having a simulation that fits 100% real life events. And yeah, so thank you very much.
All right. Any questions in the room or anywhere on the chat? I've seen that nobody typed anything. Okay, we have, of course, Igor with a question coming to the stage again.
Hi, I really enjoyed your project. So that you've done with reinforcement learning, and this is really nice that you have checked different models. So I mean training like model based and model free based. I just wonder why you didn't simply stop at DQN, because it performs really well. If you just spent a lot of time on like playing with the environment, building, and yeah, could you please explain me your experience with this selection of algorithms? That's quite interesting topic.
So we didn't even try to implement DQN because we actually needed to have on top of the value policy optimization a state value basically our model to be able to assign a value to a state. How good is that state? Because we have 5 actions and each actions like takes 4. So basically there's like 5 to the 4 basically options per action. It's way too much. So we don't have time for training, and even training for basically our case, and we managed to do 2 training sessions for 3,000 episodes, which is not much. It took 3 hours. So like relying on DQN only would take much more time and less efficient. So we did not see a point in even trying to implement it. Yeah. No problem. All right, thank you.
All right. So for the next presentation, we have Asis with a project that is actually art, but I'll let you be the judge of that. So Asis is actually doing a fine arts degree as well, and he has a background in kind of complicated, some technical stuff and some art stuff, and this is perfect because I believe that most artists are asleep at the wheel when it comes to using technology for art. And I'm not talking only generative models, but using technology the same way that you use oil on canvas or a piece of clay, right? Okay, so please.
Hi, thank you, Jose, for the kind words about complexity. Let me just, I need to share the screen, right? Sorry. Okay. And I think now we do view slideshow. All right. So as Jose already mentioned, I'm going to talk a little bit about a project that I was doing with a friend, we did with a friend. And oops, sorry, the slideshow is going by itself. And we're more interested in using the application of technology, and in this case, deep neural network in order to generate art, or a little bit more like ask questions about what you can do this, what applications you can use with this, and what it means to have a natural language generator in general. I'm gonna briefly show you the agenda. So we're gonna start with a hands-on exercise actually. Maybe Frank, you can, if anyone is missing an A4 piece of paper and some colors, you can take a couple of colors because I think there's enough colors for everyone. For those of you online, don't worry, we have a link. Maybe Mariam, you can post the link on the YouTube live stream. It's also a bit of a nostalgia, so paint from Windows back into the 90s. Then we're going to do, I will talk a little bit about why and what we're interested in how-tos. So the model basically is answering questions to how-to questions. We're going to talk about some contradictions that we find interesting, and then we will jump into some high-level overview of some technical details, memorable mistakes that we did, and then next steps, as well as some questions for the end, of course. Okay, so the exercise. Does everyone have pencils? Okay. Now, I think it's important here, you people online, please join onto this link, so you can actually do it as well. It would be super cool if you can share the screenshots maybe after doing the exercise. It's just nice to see the outcome. Don't take this too seriously. I mean, so this is, we asked the model how to draw a circle, and then the model gave an answer back. And a lot of it doesn't make sense, so be prepared to be confused. Just try to do like a movement with the hand after each kind of sentence, basically. I think just be playful. Just try to follow a little bit. There's no right or wrong way of doing this, right? All right, so the model first gave a short introduction, and then he goes into the instructions on how to draw a circle. How to draw a circle. You should only draw half a circle. Your mind should be free, and you should not draw an imaginary circle. Very important. It will be as straight as possible. And now we start with instructions. Draw a half oval shape. Draw a curve going from one end of the circle to the other. Draw a curve going left to right. Draw a circle that's halfway up from the center of the circle. Draw the angle 1 second bigger than the angle of the first circle you drew. Just keep on drawing. You can choose your own color, or you can create a simple color for a circle. Feel free to use multiple colors, by the way. In this example, we draw a quarter circle. Draw another quarter circle, one that's halfway up from the center. Make the angle 1 second bigger than the angle of the first circle you drew. It would be better if you added the lines to the circles so they are even. Draw the line as a regular 3-dimensional oval. Just keep on drawing whatever you think you have to draw. Add some extra circles or curves. You can make other shapes with the circle shape. Remember, this is an oval. We're almost there. Draw the lines on the other side. Draw the curves, starting with a little over in between. Repeat steps 3 through 7 with more circles and curves. So I will now give you a couple of seconds to finish your beautiful drawing. Beautiful, Alois. Okay, so if you did everything right, you should get something that looked like this. This, for those of you online, would be great if you can share some screenshots. Well, I guess you can't really post this on the YouTube channel, but yeah, if someone does it, very good, Frank. But anyways, we also asked other questions to the model, and some of the answers were really funny. So this is just like one sentence from the full answer. We asked the model how to create a universe, and the model replied, if you don't want to be limited by any of your creativity, you can use simple things like space, time, or other physical objects. We also asked the model how to smile, and this is actually a bit creepy. The model replied, to make yourself look more human, you'll need to grin more often. Here are some tips on how to make yourself look and act like you're smiling. And we also asked the model how to make a presentation, of course. And then on one of the sentences of the reply from the model on the generated text was, if you don't know what a presentation is, consult a professional or technical documentarian to help you understand what it is you're trying to do. But it's, I mean, the model is actually deployed on the web, and you can access it via this link. I will share the link later so that you can stay concentrated on the presentation. But I won't do a demo because I think it's nicer if you guys, I mean, I guess it's somewhere here. But it's nicer if you try it by yourselves, right? So you can type here how to boil an egg. Let's make maybe a bit shorter. It does take a little bit of time. I mean, it doesn't take too long. This is the pain of always doing a live demo. And I hope it doesn't break because there's a lot of people. Yeah, there you go. Use the handles to collect the egg yolk. Okay, that doesn't make much sense. But yeah, I would let you just try it by yourself later. Okay, but why are we interested in how-tos and what is a how-to? Actually, I think all of us here and any of you that are into tech or coding, you're very, very, very familiar with one of the biggest how-to sources, which is Stack Overflow. But basically, how-to is when we have it's kind of like a piece of information on how to accomplish a specific task. And most commonly nowadays, we either have it in the written form, but of course, if you think of like prehistory, the oral form was used very frequently through parables and singing and other ways in order to communicate culture and knowledge and information from the elder to the younger people. Of course, YouTube and WikiHow are two of the biggest data sources on how to do stuff. And this is what we use for training our model. I will talk a little bit later about the technical side, but it's actually quite fascinating. So just some quick examples here on how to do. I guess through the pandemic, making bread was a big thing. You see good old Jamie Oliver there. Sewing stuff, which is something that I guess not many of us know how to do nowadays. You can even ask more like self-help stuff as how to be happy, which I mean, I have definitely problems with this because what's the definition of happiness? You can even ask YouTube or a WikiHow how to be a millionaire. But I guess if it would work better, most of us would be millionaires by now. But what I really find fascinating is all of these weird things that YouTube has to offer. And I actually found this accidentally. And there is this dude that manages to balance 3 eggs on top of each other. And there's a video about this. And, you know, this is something amazing. This is something that as artists, we find fascinating because it's just people doing stuff. And thanks to the internet and technology, this is accessible to the wild world, to the worldwide, as long as there is no, what's it called? Anyways, filter cutting your access to YouTube. So yeah, we find this very interesting, and that's why we wanted to work with this. But of course, there's a bunch of paradoxes with how-tos in general. One of them is, if you think of these two articles on WikiHow, these are rather very simple things, but they, in order for us to access this, there's so much technology behind this, right? So you have like the website, you have a server, you have the internet, you have wired cables, and all of this, it's really, really complicated technological setup in order for us to access such simple information on how to do something. Another paradox is that we are really, I think most of us here wouldn't be able to make fire without a lighter, right? Even though we use fire every day, there's this kind of milestones for the development of human intelligence that it's not really relevant nowadays. And we find it kind of interesting and somehow absurd that an AI will tell us how to make fire when it's, you know, this big milestone for humans that we've achieved. There's a very nice quote by the good old Carl Sagan, which says, "We live in a society exceptionally dependent on science and technology, in which hardly anyone knows anything about science and technology." And this is really a big problem, right? I mean, at least those of us that grew up in the 90s, we know about a little bit about, you know, HTML, playing around with MySpace, or folder systems, you know, executing apps to open the Age of Empires and this kind of stuff. But the newer generations, they definitely more focused on phones, and they don't really understand what a file system is, for example. And this has many problems. When people don't understand technology, I think it's more easy that people get, yeah, I mean, manipulated in some ways maybe, or just it can be a bit dangerous for in many ways. But I think, I mean, the previous presentation that we talked on the bootcamp, we talked a little bit more about this politics and AI. But just as a summary, we're very interested in this interconnection of culture, technology, and reality. And obviously, technology is gaining more and more strength in the shaping of reality, right? And when I talk about reality, I'm not talking just about us humans. I also talk about the entire planet and probably soon the universe, right? If Elon Musk goes with his projects. And this is something very interesting to think about and how this affects us. And obviously, as technologists, we also have a responsibility and think of the implications of the products that we're building on the world that we live in, right? And this is something that we want to explore. And building this model, I mean, I guess in 3 weeks was one of the ways to start this exploration process. So technical details. Marian, maybe you can share the link also on the on the YouTube. Oh, okay, cool. So this is the link for the you can try yourself if you're not so interested in the technical details. If you are, I will share it again in the end, or it's already on the YouTube channel. But yeah, so this is a very high level overview of how we made the model. We used a sample of 25,000 WikiHow articles. And first, I played around with a T5, which is a sequence-to-sequence model, the small version. I think it's 60 million trainable parameters. And also tested it with GPT-2, with the base one, which is the double pretty much of it. And actually, GPT-2 was performing a lot better. I think it felt a bit more human and natural than T5. So that's why we decided to stick with GPT-2. And this is the model that it's still this beta one. Maybe you can't see it, but it's here, this beta one. This is the model that is actually deployed. The larger model is still training, the one in green. So yeah, we will probably deploy it by the end of the week. Once the model was built, we used Fast API to create an app that we deployed on AWS to serve on the API for the website. So the website the front end is done with Express, and the server side is done with Node.js, and then it's deployed on Heroku, and it's taking the sending a GET request to EC2 from Amazon to get the response to send and to get the response from the model, basically. This is just a very high level overview. I mean, we're very excited to see how the large data set works, actually. I mean, it takes around 10 hours for each epoch, so it's really, really slow. So memorable mistakes. First one, underestimating training time. Again, you know, I should have started running the model earlier. Last week, I was pretty much just focusing on deploying to AWS, which wasn't easy by itself. So the model could have been running in parallel. Checkpoints, really big mistake. I didn't set up checkpoints because I thought maybe I could take one of the latest checkpoints from the model and use that. But no, there's no checkpoints. So very bad. I will never do this again. I really recommend you guys to check out checkpoints. You probably all did because you're a lot smarter than I am. The no freelance theorem, also in the literal way. There's no way. We tried to deploy this for free, but Heroku offers up to 500 megabytes, which the model is heavier than that, so we can't really use that for free. So be ready to pay if you want to do any serious deep learning, which is fine. Either by using GPT-3 or AWS or any other Colab or whatever. There's already many data sets there. So I spent, I guess, around 3 to 4 days setting up a scraper to get the WikiHow data, which is this sample size that we use with 20,000 data points. And then 1 day later, I found out that somebody already scraped the entire WikiHow and you could just download the CSV file. So I was like, okay, great. It would have been nice to know that beforehand. And opening the ports, yeah. I mean, I spoke with Marcus about this, but I had some issues with opening up ports. It's really something for magicians to know what port is open on AWS when you're just looking at terminal, you know. Just a quick brief of some to-dos. Would be really interesting to test with the YouTube. The problem with the YouTube is we're using the API that gets the script, the transcript of the script, and often it doesn't have punctuation marks. So this is an issue. Tristan suggested actually that we could fix this with GPT-3, which it has a corrector that would actually, we tested and it works really well, but again, not necessary for the MVP. So this would be like a further iteration. More text cleaning would be also good. Fine tuning, we had no time for fine tuning. The code is a mess, I have to say, and I would definitely like to use the fast AI wrapper from PyTorch, and maybe also test the large data set with T5. Deployment wise, we still need to set up some HTTPS. I could not manage to get Docker to work, so it would be really nice to try that out. And I'm not sure if there's any way that I can increase the instance performance. Probably, I guess, getting a faster instance. Front-end wise, also a few things to do. We don't have a web hosting, as you already saw. And from the art perspective, I mean, what we're interested in is kind of materializing this content that is being generated by this AI, right? So all of this is digital, and I find it very interesting when it somehow gets materialized. One way is by the performance that we did just now, that all of you draw something, and I'm really keen on taking this with me. And as a documentation of artistic practice. Making videos, how-to videos. We were thinking of maybe asking the model how to make a table and then recording a video and mass making a table. Or maybe even publishing a book or a small publication with some question and answers that we find are interesting. Oh yeah, next projects. So definitely image in painting. Antonio, if you're there, I'm going to be reaching out. And reinforcement learning for our chess-like game. Hey, Nima. Salam. I will also be reaching out. Last final remark. I had one of these silly ideas the other day, just today, and I thought, okay, so it's taken 250,000 years for humans to develop language. And it's taken 40 to 50 years for neural networks to develop language. And I was thinking, how would neural networks look like in 249,950 years from now? So I will leave you with that message as a goodbye. And thank you for your time.
All right. Is there any question in the room? So I see Igor raising his hand already, coming in. Okay, yeah. The question is, did you enjoy this project?
Well, yes and no. I mean, it was definitely a lot of stress. 3 weeks is not much time. And I think I spent 3 days struggling with a bunch of things that there was no results. You know, like programming is this carousel. So sometimes you get things done and there's a lot of excitement and you feel like great. But if you for too long don't get this, then it's really depressing, to be honest. And you can only pray that you do the next day you can fix something so that you get some motivation back. Any other questions?
All right, so I don't know how the experience was online, but here at the DSR office, I've never heard so many people laughing so loud. So there is something to be said about this type of projects. Okay, for the next project, we have Alois and Frank that are building a tool. So this is actually one of those projects where you can see already a commercial application at the end, and it looks the part as well. They're building a tool for people to learn second language. And if you are like anybody in Europe, you probably have experience learning second languages. Your experience may not have been great. So they are trying to solve that problem. So Alois and Frank.
All right. Okay. Hi, everybody. My name is Frank, and this is Alois. And we're very excited to talk today about our project Nova AI, which is a conversational AI for language learning. So I'm first going to tell you a bit about the motivation and how we came up with this project. If the clicker works, but it doesn't work, I have to aim at this. No, it doesn't work. Ah, does it work now? Okay, now it works. Okay, cool. So learning new languages is a very important skill in our world today. There are roughly 1.8 billion people that are learning languages, and English chief among them. And I think many of us can relate to that because, well, we all speak English right now, and many of us have learned it as a second language. And actually, many of us use it every day for work. Among Europeans, 53% use a second language at work. And being able to communicate well in this language is often very important in order to be successful at your job. All right, so languages are important. So how do we learn these languages? So I want you all to think back to how you learned English for the first time. And probably it looked something like this, right? So at school, in a classical classroom setting with textbooks, a teacher in front of you throws vocabulary and grammar at your head until it sticks and you can speak the language. So this is kind of like the brute force approach to language learning, right? And actually it is quite time consuming. In Germany, in fact, we have up to 10 to 13 years of English classes in school, starting from first grade or third grade. And yet only 42% of students can communicate in English at an intermediate level once they leave school. So clearly something is not really working well here. So the problem is that traditional classroom learning, it is very time consuming. And it is very focused on grammar and vocabulary lists, and it is very passive. And well, research has studied this, and they've shown for a long time that what's missing, the crucial part, is that in order to be good in speaking in a language, you have to be given opportunities to actively talk in that language. I think this makes intuitively sense, right? The first time you're in a situation where you actually have to speak in a language, that's a whole different challenge. All right, so this is not ideal. So how can we improve this? So, okay, so technology to the rescue, like, right? So language learning 2.0, now we have all these apps, Duolingo, Bubble, super easy to get started and learn a new language. So I want a quick show of hands. How many of you have ever downloaded one of these apps or a similar app and started learning a language? Okay, so a lot of hands going up, almost everybody. Okay, great. So follow-up question. How many of you have ever completed a language course in one of these apps? One, actually. Very good. Okay, so one person. So the others, you don't have to be too bad about this. Actually, informal studies suggest that only around 0.01% of people that start a language course on Duolingo or Spanish actually finish the course. So 1 in 10,000. So clearly something isn't working here either. So what's the problem? If you look at it, these apps actually replicate a lot of the mistakes of traditional language learning, which is they're very focused on vocabulary and grammar. They have interactivity, but it is often limited to very specific patterns like select this card or repeat the sentence. And it's still artificial learning in a vacuum without the natural context and the natural conversational environment. All right, so to summarize the problem, the way we currently learn languages is often inefficient because students are too passive and they're not really encouraged or don't have room to use the language for communication. But actually, modern technology allows us to tackle this problem. There are now these language models like BERT and GPT-3, where you have seen great examples today, what they are capable of. They're easily accessible via platforms like OpenAPI or Hugging Face. And they can be used, for example, to generate dialogue like this, which already seems very realistic. And so our idea was, what if we can use these models to simulate a realistic and conversational environment for language learners that they can use to practice in? And this was the base idea how we came up with the project, with the Nova AI project. So our goal, our mission statement was to create an application for a conversational AI that users can talk to and thus gain fluency in their target language.
All right, and Alois is going to tell you now how we continued from this initial idea.
Thanks. Yeah, I'm going to walk you through our process. So once we had our mission statement, we started to invest in our problem defined. We started to investigate which technologies would actually help us solve this problem and what features would be useful to the users. Once we had some ideas, we took part in this innovation workshop here at DSR, which allowed us to break down those features into smaller manageable parts. We then plotted them on a feature complexity matrix to see how much effort is needed for each feature and which features can be the most valuable with the minimal effort. And this allowed us to prioritize and to create our roadmap and milestones. So this is what our roadmap looks like. We had 3 weeks to complete the project, so we divided it in 2 milestones. Our first milestone was to achieve a minimal viable product. You can see here our main features was a simple conversation mode, a browser text interface, a basic grammar correction, and we wanted it to be deployed on server. Once we did this, we moved on to the extended prototype with an extended website, just meaning a more beautiful front end. And then we wanted to focus on making this language learning model really, this model really language learning oriented. And then we added some adaptable language levels, some specific scenarios, and some personas. What does the model actually look like now? So this is our language processing pipeline. When the user chats with Nova, the sentence from the user is first fed into the grammar model. There, the grammar model decides whether there is an error present in the sentence, and if there is, it will output a correction message and also store information about the error for further analysis and feedback. And then this sentence will be fed into the language model, which then will generate a dialogue response. So you can see here, I go to a movie yesterday. It's corrected into, I went to see a movie yesterday, and then the model generates a response. Cool, what movie did you see? Let's go a bit more in depth into our actual models. So for the grammar model, we use a pre-trained model from Hugging Face called Gramformer, which is a GPT-2-based transformer trained on Wikipedia edits, which is trained on grammar error detection and correction task. You can see on the right side, the right side, in yellow are the error types classified, and in green is the error correction. I'll give you a second to have a look. I hope that the slides are synchronized. Yeah, okay. Well, in theory, this is all great, but as you all know, in practice, it's very different. So we actually run into some challenges, and those are 3 of the main challenges that we run into. The first one is that the corrections that the model outputted sometimes were not actually errors. They were more like suggestions for alternative way of saying things. Another issue was that our corrections were not necessarily always the same. So the user could say the same thing twice, and the model could output something different. So once he would tell you there is an error, and once he would tell you there is no error, which can be quite frustrating for a user, right? And our third and main issue was that the model actually was quite strict with the corrections, especially when it came to punctuation errors and capitalization. And per se, those corrections are perfectly valid, but if you are a person who likes to chat, you most likely, I imagine you don't really always have a correct punctuation or capitalization. And this in the end really hindered the user experience because it broke the flow of the conversation. So we decided to modify the pipeline of this model in order to just enhance the user experience. What we did is we decided that if there was an error in the sentence of the user and the error was only punctuation capitalization, we would not output a correction message. And then as a fail-safe, we also implemented fuzzy string matching, meaning that if the user inputs and the corrected sentence would be similar above a threshold, we would also not output a correction. And this is an example of a proper grammar correction and then generation of further dialogue. Yeah. Let's move on to the language model now.
All right, so for this part, our goal was to create a good conversational response to the input of the user. So first we used a model called BlenderBot. So this is also a GPT-2 based model and specifically trained to be good at dialogue. It was trained on a dataset called the Blended Skill Talk dataset, and the aim for this model was to be especially good at having an engaging conversation and being very empathetic to the users, which is why we chose it also. So here on the left-hand side, you can see an example of what the chat looked like in the first iteration. So you see it's quite a reasonable dialogue. So what we found is that the model worked quite well. It produced good, engaging conversations. It was good at keeping the conversation going, especially, which a lot of language models don't do. And it was fun to talk to. It had a joyful tone. also good with a dialogue-specific trained model is it has a consistent response format, so we can always rely on it's a good dialogue response. And the model we used had only 400 million parameters, and we could run it on a local machine without much problem. The problem is also, it is a very small problem, a very small model. So the quality was so-and-so. It often got stuck in a loop or started contradicting itself. And running a bigger, more powerful version would have been more costly to run and require a GPU and some investment in infrastructure. And also the model had a quite static persona and was not easily customizable without fine-tuning it. So for our second iteration, we decided to switch to GPT-3, which is a lot more powerful. It has 175 billion parameters. And you have seen some of the examples how it is more powerful already today. So I don't want to go too much into depth about the model. So this is kind of just an explanation how we used it. So we always had a base prompt that told GPT-3, basically, this is a dialogue, please give us a good response. And then we appended the dialogue so far. So for example, the first message from the user here. And then we sent this to the API, generated a response, fed that back to the user, and then got on the next input from the user. So this was our core loop. And based on this, our goal was to create 3 conversational modes for our application. So first, we wanted to offer a general conversation, an unguided chat with our Nova AI about any topic you want. Then we wanted to implement scenarios where you could really simulate a specific scenario, for example, shopping in a store or ordering at a restaurant. And in that, Nova then assumes a certain role, like the store clerk or a waiter. And then we also wanted to experiment with personas, where you can chat with a really a specific person from history or from fiction. So first, for the general conversation, this is kind of what the base prompt looked like. So we tell GPT-3, this is a conversation between a human and Nova, and she wants to help the user learn English and so on. And here on the right-hand side, you can see an example of what this kind of looks like. So you can see apparently Nova doesn't like Batman very much, but she likes Superman. Yeah. Based on that, one thing we wanted to offer was adaptable language levels. So when we found out we could also do that quite well by just modifying the prompts, and a lot of can be achieved with good prompt engineering. So here, for example, for a beginner level conversation, we told Nova, you speak beginner level English, you use short and simple sentences and words. And for an advanced prompt, we told her, yeah, talk in a more complex fashion. And here, for example, you see an example of the advanced chat. So here you can see Nova asks more questions and has very interesting opinions. Like she thinks Batman is a hero. He fights corruption and abuse of power in Gotham City. Yeah, you can have interesting conversations there maybe. All right, so this was the general conversation mode. And then also we implemented these scenarios. We implemented 3 different scenarios, buying bread at a bakery, shopping at a store, or ordering in a restaurant. And for that, we always told Nova, you are the baker and you sell bread, for example. And here you see one example of this. And yeah, and for the third mode, we wanted to implement the personas. And Alois will tell you about that.
Yeah, thanks. So first, we thought the prompt works well. Why not try this out that way? So we tried here to implement personas via prompts. In this example, we used Harry Potter. We told the model this conversation with Harry Potter, and then asked it who's your favorite teacher and who are your best friends. And you can see that the model knows quite well about Harry Potter, knows that Dumbledore is a teacher, and that Ron and Hermione are the best friends. However, it does not necessarily copy the style of the character, which was what we were intending to do here with William Shakespeare. So we told the model, you are William Shakespeare, and it ended up just outputting just results from the internet about information it had about Shakespeare, which was not super interesting for us if you wanted to really pretend we're chatting with William Shakespeare. So we figured, let's try to do some fine tuning. I will not go in depth with this because this is the same as the first presentation that you had today. But we fine tuned GPT-3 on with two different models. We tried with Ada and with Curie. Ada is a small, fast model. Curie is a bit more complex. And the way we did this is that we fed it 5,000 lines from Hamlet and Macbeth. And we just saw how it worked. So you can see in example 1 with Ada, the smallest model. We asked Shakespeare, how are you doing? And the answer, well, looks quite Shakespearean, but it's also nonsense. yes, it just meant nothing. The part that's cut was also nonsense. But it's pretty fun to look at. In the second example with Curie, the model gets better at dialogue, but we lose a little bit of this format. So we can see in the first model, it was less good at generalizing, which in the end made the formats and I think the topics come out a little bit more, but it was just not a nice thing to talk with.
All right, and last, we want to show you the application that we built in the end. So our goal from the beginning was to really build an application that language learners or users could use for language learning. And so that's what we did. So this is the basic architecture of the application that we have. So at its core, we have a Flask application, which has the grammar model and the language model, for which we used first BlenderBot in the first iteration, and then we used the OpenAI API. We have a database where we store some user info from authentication and so on. And then the whole thing was deployed as a Docker image on an AWS EC2 server. And a user can access our application via a web interface. Yeah, so this was kind of what the first version looked like. And we had that up and running at the MVP stage. So this was just the bare bones application with a general chat for us to test something. So there's some random stuff in there now. And then after the first iteration, we wanted to redesign the front end and make it a really good application. So we did an outline of the sitemap. We thought about the user flow, how a user would use the website. We designed some wireframes for the different parts of the website, like the main dashboard, what the chat should look like. And yeah, based on that, we implemented this. And now we're going to do a live demo. So our application is online at nova-ai.net. So go there, try it out. Yeah, so this is kind of what the landing page looks like. We have some information about the app, yeah, what the features are that we offer. All right, and when you click on Get Started, you're redirected to the user login. So it was important for us to be able to offer a user personalized, customized experience. So that's why we implemented this. So here you land on your dashboard, which shows you some of your recent progress and also suggests something to do in the app. If you go to learning statistics, you can see more about your learning progress. So the recent sessions you had. And here, for example, we show the grammar because we can store info about yeah, what things you're struggling with and show you feedback here. And based on that, also suggest some next chats that you could do, for example, here. All right, so yeah, let's go to all chats. So these are all the chats, conversation modes that we've implemented. So at the top, you see the general conversation mode, the unguided chat at 3 different difficulty levels. Then below that, we have the 3 scenarios that we implemented, and then our Shakespeare persona so far. So if we go to one of the scenarios, maybe the bakery, just to show the interface. So that's kind of what it looks like. Here on the side, you see a small description about what the scenario is. And then something we found out, it's good if we add some goals that the user can achieve and try to achieve in the conversation. For example, buy 6 slices of bread. And that gives them something to do. In a later iteration, this could also be detected from the user text, whether they have really achieved that. All right, and now we're going to try it out. We're just going to go to the intermediate chat. So you can see Nova always starts with something like, hey, how's it going? And so on. And now, yeah, Aloise is going to tell her that we're talking about her. Right, so and once you click send, this gets fed through the grammar model, sent to GPT-3, and yeah, Nova is happy that we're talking about her. All right, so does anybody have any suggestion what to say? Let's see, let's try to break it. Which kind of pizza was ordered? Oh, that's interesting. Maybe she'll know that no pizza was ordered. We should order pizza. That's a good suggestion. Yeah. Let's tell her to order pizza. I'm sorry, I don't understand. Okay. That seems like she really rarely says that. So maybe she really picked up on that. There was no pizza ordered. Something else? What do you like to do? Okay, what do you like to do for fun? Yeah, sure. Let's See, I like to chat with people. See, we trained her well. Yes, of course she does. Are you what? Are you Captain Obvious? I don't know if she know what Captain Obvious is. Let's see. I think you mean, are you a captain? So you see the grammar correction kicked in. She obviously thinks Captain Obvious is wrong. And she's, again, doesn't understand, really. Interesting. We never got her so confused. You're asking very confusing. What's your favorite meme? Oh, okay, that's interesting. I don't know if she knows what a meme is. Yeah. I don't know what a meme is. She doesn't know what a meme is. Oh, that's too bad. What's your favorite joke? Oh, that's cool. I don't know if she has any jokes saved. What's your favorite joke? She doesn't know any joke. Okay, she's being very boring here. Okay, we're gonna tell her to be more interesting in the future. Does she know Siri? Is Siri her friend? Yeah, okay. Let's see whether they're connected in the background somehow. I don't know who Siri is. Oh, okay. No, that shouldn't change it actually. How do you like your creators? How do you like your creators? Okay, Nova has to get this one right, or we shut her off. We'll stop the server. I don't know what you mean. Oh, that's interesting. Oh, maybe it's because now in the chat history, we have so many, I don't know, examples. Yeah, yeah.
She does remember the chat.
You have to click in the address bar. Yeah, if you do that, then it resets the chat. How do you like your creators? So does it mean that the response is based on the previous? Yeah. Oh, I like them. They're nice. They have helped me to learn a lot of things. Okay, we stop here now. That's the end. It won't get any better than this. Yeah, but one interesting thing we saw here is, so we give her all of the previous chat as input. So probably she also, yeah, she had all her previous answers of I don't understand, and maybe she tried to replicate it then for the next input. So that's very interesting. Yeah, so that would be maybe an improvement to, yeah. Yeah, so that's also something that we would like to tackle to, yeah, separate this maybe, that it knows what the user said, what she said, and so on. All right. So back to the plan. So this was our road so far, and we just want to give a quick outlook what we could do next. So we want to further improve the dialogue quality. As we saw, there are some kinks that could be leveled out. We would also like to try the Blender bot model again, or our dialogue specific model again, because we also got good results there. The tracking of grammar errors we have not yet fully implemented. This was more like a mock-up that you saw, but we could store these errors and show them to the user. We want to implement user goals and ranks and more of the learning path system so that you can really use it to learn. And for that, also, we want to add more scenarios and more personas. We also really wanted to implement a speech interface because that would be a really great experience to not have the chat, but also actually be able to speak. And then we want to extend it to other languages. So that it's not just for English learning. All right, so again, the application is online here. Go there, make an account, try it out. We also have the full code for the application available on GitHub, so you can also look at that if you're interested in this. And here are our contact details. If you have any questions or wish to contact us, yeah, you can contact us there. Okay, cool, thanks.
All right, any questions? No. Yeah, come on. Oh, yes, what's what? Okay. By the way, this is an example of a full project that could be a commercial application by the end of TSR, which is always the aim, what I recommend people to do. It's super hard, but this is a proof that you can do it. So.
First of all, thank you. That's really nice project. I really like it. I wonder, so you were working with GPT models, and transformers are really scary stuff. That's huge, that's massive, and that's like not everyone there to just start to work with this. What is your experience? Did you really start to directly work with transformers? Or like you first of all tried some simple models and afterwards someone convinced you that it is fine, let's just start, take it easy. Yeah.
Yeah, so we started right with transformers, but it's also because like transformers are now the best out there that there is. And so the first model, BlenderBot, was a transformer-based architecture. GPT-3 was also a transformer architecture. But also a thing is nowadays the software as a service platforms, machine learning as a service has become so advanced that you don't need to like be fully deeply into knowing the architecture of GPT-3, for example. The way we use GPT-3 via the OpenAI API, it's actually really simple. There's a good documentation. You send in the prompts, you send it in the correct format. You can do some manipulation of the model if you want to. But yeah, so to get started, there's not that much knowledge required, which was really good. Yeah. Yeah, Oscar.
How about different languages than English?
Okay, so question about different languages than English. So GPT-3 and most of these language models are trained on English predominantly, which is because most of the research is happening there and the largest corpus are assembled there. I'm actually not 100% sure how multilingual GPT-3 in particular is. And yeah, but that's really an issue. There are not many models that are specifically trained for other languages. So one thing that we actually wanted to try out to extend it to other languages was to try and use DeepL, which is available via an API, to do a translation and then try out whether that works. So yeah.
Yeah, just to add something. So for example, the grammar model works with Spacey, which has some really good other language models for other languages. So that could also be applicable. And we would have to change things like the capitalization that we removed is obviously important in German, for example. So we'd have to change things like that.
Closing words. So very well done. This batch really had a big challenge. We've been around for 8 years. There are 200 and something projects done. It's hard to come up with new ideas, but you have done it, and the things that you've done are really innovative, and your creativity is like off the charts. So I'm really happy to see this, right? It also proves that you can do a lot of stuff with the current state of the art of machine learning. And it's a mystery to me why companies are not doing this and actually making money, right? Because for anybody watching this on YouTube, look at what you can do in 3 months, right? If you are a corporation with billions in the bank, why are you not doing these things? I don't know, right? Okay, that's one point. Another point is you may have seen that there are many projects using NLP. That used not to be the case a year ago, right? So computer vision projects were all the rage, and now in this batch, there are pretty much no computer vision. Like there are a lot of projects with NLP and a lot of projects with audio. That's a good sign, right? So there are more things that we haven't tried, and it's good that the tooling for NLP is now such that you can use it for production apps, and it actually produces good quality stuff. That is very impressive. It opens the doors to many applications that we don't have right now, that we are not doing, right? Still, the big question mark is why are companies not doing this in production, right? Because look at what is possible in limited time with limited resources while you are trying to learn this stuff and making a project that solves a real problem, right? And there are projects here that look like a real product that you could start using, right? Why is this not happening in industry yet? If you know this, send me a message, an email, whatever. I want to know more about this. If you're in a company right now and you're scratching your head, why are we not doing this? I'm with you. So what can we do to support you so you do this in your company, right? Okay, so thank you very much for surviving with us for 2.5 hours. This was a long stretch. So thank you for your attention, and hopefully we'll see you again in the next batch presentation day, demo day. Thank you.
duplicates. We normally give you a bigger Photoshop.